Welcome to RStreetTech. This is Ritesh Srinivasan. In this video, I will demonstrate how we can implement text classification using neural networks using TensorFlow 2.1. I am specifically training a simple neural network for text classification to classify sentiment of tweets. I'll be using the TensorFlow GPU version. If you are new here and if you like such content, please subscribe to the channel. Let's get started. Let us look at how we can implement text classification with TensorFlow. TensorFlow is an end-to-end open source platform for machine learning. It has a comprehensive, flexible ecosystem of tools, libraries, and community resources that lets researchers push the state of art in machine learning and developers easily build and deploy machine learning powered applications. The dataset is from the tweet sentiment extraction challenge from Kaggle. We would implement text classification using a simple neural network developed using TensorFlow on tweet data to classify tweets as positive, negative, or neutral. Let us look at how the trained data looks like. So here you have four columns in total. We have the text ID, the text, the selected text, and the sentiment. I will not be looking at selected text because we are just looking at text classification over here. So the idea is that given text like this, for example, this is a tweet, given tweets like this, right, and their sentiments, right, in training data, we would like to classify new tweets as belonging to either of these categories. Now let us look at our test data. Again, we have three columns over here, the text ID, the text, which is the tweet text, and the sentiment. So basically, we are actually now trying to predict this sentiment for this particular tweet. For example, if the tweet is this, it is a positive tweet. So we should be able to predict, given this tweet on a trained model, we should be able to predict that it is a positive tweet. Let's start by importing the necessary libraries. So for TensorFlow, we use import TensorFlow as TF. That's how we import the TensorFlow libraries. We also import other libraries from TensorFlow, like from TensorFlow Keras, layers, losses, and regularizers, which I'll be talking about later. Then we use NumPy and Pandas, and we also use some methods from the sklearn preprocessing or sklearn scikit-learn packages. Okay, now the TensorFlow version which I am using is 2.1.0, and I also have a GPU device, so I am using the GPU version. First, let me define some methods to pre-process the tweets. So I have emoji removal, URL removal, and punctuation removal as pre-processing methods. Now let us import our trained data, and we do some pre-processing on the trained data over here. We also do some pre-processing on the test data. Now let us look at the distribution of the trained data. So you see over here that we have close to 10,704 neutral tweets, close to 8,375 positive tweets, and 7,600 negative tweets. In total, we have 26,752 tweets in our training data. In our test data, again the distribution is like you have 1,376 neutral tweets, you have 1,075 positive tweets, and you have 983 negative tweets. In total, we have 3434 tweets in the test data. So now we have pre-processed the training and test data, and the next step is to get them ready or convert them in a format which will be accepted by TensorFlow. So what we will do is that since we have only the train and test data, I am splitting the train data into train and validation data using the train test split function from a scikit-learn, and I am splitting it in the following ratio. So the training data would be 67% and the validation data would be 33%. I also use stratify method so that, because if you look at the distribution of the classes, they are slightly unbalanced over here. So the stratify method will produce a balanced distribution of the classes. Okay. Now to process the text, we need to convert it as an NumPy array. So we do that conversion over here. So we convert the train tweets, we convert the validation tweets, and we also convert the test tweets. The next step is that if you look at our class distribution, you have these labels positive, negative, and neutral. Now, to convert it into a format which can be accepted by TensorFlow, we need to convert these text labels into categories. So for that, I use the label encoder again from scikit-learn to fit the labels on the the training data. So the sentiment column from the training data. And what I do is that I will apply also the transform function to convert the labels into categories. So that is a conversion which happens over here. Uh, then similarly, I do it for the validation labels as well as for the test labels. And then I create a TensorFlow dataset. So this TensorFlow dataset I create by combining the tweets as well as the associated labels. So now I have created a TensorFlow dataset for the training data, for the validation data, and the test data. Let us look into detail how we convert the training classes or the class values into labels and then to categories. Okay. So first we use a label encoder to fit transform on the text values. So if you look at the text values, you have the tweet categories as neutral, positive, negative, right? So these are the first 10 tweets in the trained data. So once we convert it into labels, neutral becomes 1, uh, negative becomes 0, and positive becomes 2. And once you convert it into a category, neutral or 1 becomes 0, 1, 0. Positive, which is 2, becomes 0, 0, 1. And negative, which is 0, becomes 1, 0, 0. So this is how we convert from text category values to categorical values, which can be then used in our multi-class classification by TensorFlow. Let us now print some samples from our train, validation, and test datasets. All three of them are TensorFlow datasets. So you can just iterate over the dataset using a for loop, and you can print the contents of the dataset. So for in our case, we have two columns. One is the text and one is the label. So here you can see that the text is a tensor of type string, and you have the string. And then you also have the label, which is also a tensor. Its shape is 3, and it is of type float32. So these are samples from our trained data set. Then we have samples from our validation data set, and then some samples from our test data. Let us start building our model or our neural network using TensorFlow. So the first step is that we have input text which needs to be converted into vectors for our neural network to process it. So this layer is called as an embedding layer, and we can have it as our first layer in the model. So the embedding layer, the advantage is that we don't have to worry about text processing, and we can benefit from transfer learning. So in this example, I have used a model from TensorFlow Hub. The model is called as GNews Swivel 20 dimensional with out of vocabulary. So you can look at further details about this model from this link. Now what happens over here is that we can create an embedding layer like this. So we call it as hub.keras layer. We specify which is the model, and we say it is trainable, so it can also be trained as part of the entire neural network. So what this model does is that, given this text over here, just getting additional free, this text is converted to this 20 dimensional vector value. So this is what happens by using this embedding. Let us create a simple neural network with TensorFlow. For that, we use Keras, which is a high-level API, which makes it easier for machine learning beginners as well as researchers to create models. It is integrated as part of TensorFlow 2.0 onwards. So I am using the sequential model. A sequential model is a simple model having a collection of layers. To know more about Keras and sequential model, you can look at this particular link. So here I am creating a neural network model. So I instantiate the model by calling model is equal to tf.keras.sequential. So this instantiates the model. Then I add the layers. So the first is the embedding layer or the hub layer, which we have defined previously. Then the next layer is a hidden layer, simple fully connected hidden layer of neurons. So the fully connected layer is your dense layer. And I have 10 neurons over here, and the activation function for these neurons is ReLU. Then I have the output layer, which is also of the type dense, again another fully connected layer. I have 3 neurons for each of the classes, and the activation function here is sigmoid. So if you do model.summary, it actually gives you details of the model, and then when you do model.compile, it actually builds this model. So for training a neural network model, you need a loss function. So because our data is categorical, so we have 3 categories: positive, negative, and neutral, and we have converted it into categorical values like 100, 010, and 001. We use this categorical cross entropy as the loss function to train our neural network, right? So the loss function is categorical cross entropy, and then we do back propagation to actually train our neural network. All this is internally taken care by TensorFlow. We need not write any explicit function. And for optimizing the weights via back propagation, we use the for minimizing this categorical cross entropy loss, we use the Adam optimizer. And the metrics which we are interested over here is categorical accuracy for the classification. Okay. Now, when we do the model summary over here, we see the model is printed out over here. So basically, it's a sequential model, so it gives a name to the model, and then you have the layers and the output shapes and the parameters or weights. So the hub layer as an output of 20 dimensions or 20 dimensional vector or a tensor, and the total number of parameters or weights at the hub layer is, or the embedding layer is 389, 380. Then we have our hidden layer. So the hidden layer has close to 10 neurons. So the output layer of the previous layer had 20 outputs, basically 20 dimensional outputs. So the number of parameters for this layer is 20 into 10, which is 200 weights, fully connected 200 weights. And then you have 10 biases. So 200 plus 10. So we have 210 parameters or weights over here. Now from this dense layer, we are connecting it. We are having this output layer, which is also fully connected. So you have 10 neurons over here. You have 3 neurons over here. So the number of weights required over here is 3 into 10, 30 plus 3 biases. So we 3 weights for the biases. So we have totally 33 weights or 33 parameters. In total, this network has 389, 623 trainable parameters. This is a very simple neural network. So the number of parameters are huge because of this embedding layer over here. Okay. We can also plot this model visually to see how it looks like. So we have the input layer, which we did not define, but it is automatically taken care of. Then we have also we are not mentioning any input size or dimensions over here. But from this hub layer, we know that the output dimension is 20 bit vector, and the output dimensions of the dense layer is, it takes this input as this 20 bit vector, and because we have 10 neurons in the hidden layer, we have 10 outputs from the hidden layer. Then we give it to the output layer. So again, we give the input as 10 what you call 10 numbers, or which is multiplied by 10 bytes or something, and it goes to this output layer, and the final output is three. Basically, we have three neurons, so you get three outputs over here. And again, based on the probability values, you can say that whichever is the highest probability, you can say that the classification is done for that particular class. Okay, so if the weight, if the first, if one stands for over here, or the first neuron stands for the neutral, two stands for negative, and three stands for positive. If the probability value is highest in three, then you can say that the tweet is being classified as a positive tweet. Okay, so now let us train our model. So we define a parameter called as epoch. So basically an epoch is that it runs over the entire data, right? So that is an epoch. So when the learning model tries to fit the data on the entire data, you call it as an epoch. So I want to do it 20 times over here. So the epoch is 20. So all I need to do to fit a model on our data is that I call this model.fit function. I pass our trained data set, and I also say that we can shuffle the trained data set. I want to train on batch sizes of 128 for these many epochs which I have defined, and the validation data I am passing the validation data set. Okay, so this is how I instantiate and I also train a particular model, and we can get the metrics and values from this model during the training process and store it into a dictionary called history. So as you see over here, it says train for 141 steps and validate for 69 steps. So if you multiply this 141 into 128, which is your batch size, you will get the size of the total training set. Similarly, if you multiply 69 with 128, you will get the size of the test or validation data set. Okay. So now when we do the training in the very first epoch, you can see that the categorical accuracy of our classification is 0.45 and the validation accuracy is 0.56. Okay. So if you look at over here, the validation accuracy is much more than the training accuracy. This could be because the validation dataset has very simple examples compared to the entire training dataset. Okay. Now it trains like this, and epochs are completed. So we have at the end of say 20 epochs. So at the end of 20 epochs, we see that the categorical accuracy on the training data set is 81, but the validation accuracy is only 0.64, right? So now let us see what is there in the history variable which we have created. So history variable is a dictionary if you look over here. So it has the loss functions. So I actually did not mention the loss function over here. So you can see that the loss has been optimized over here. So it starts out with a loss of 1.0498, and the loss starts, the training loss is decreasing, and by the end of 20 epochs it is 0.73. Similarly, the validation loss also decreases. Sometimes it increases a little bit, but this is how a neural network learns, right? Now, if you look at the history variable, you see that it is a dictionary of the losses for each epoch, the categorical accuracy on the training data for each epoch, and the value of the validation loss for each epoch, as well as the value of the categorical accuracy for the validation dataset for each epoch, right? So this is what is stored in this history dictionary. Now we can plot this validation loss for both the training and validation data. So this is what I show over here. So if you see over here, the training validation decreases quickly, but the validation loss for the basically the validation data, or the loss for the validation data, does not decrease as much. So you can see over here there is a huge gap between the validation loss and the training loss. So actually the model is actually overfitting over here, right? It is overfitting on the trained data. So now we can plot the accuracy as well of the categorical accuracy of the training data versus the validation data. If you look at again the training data versus validation data, the accuracy you see over here is that the training data accuracy is huge at the end of 20 epochs, whereas the validation accuracy or categorical accuracy for the validation data is somewhere around 65, whereas this is somewhere close to 80 or above 80, right? So this is definitely a model which is actually there is overfitting over here in this simple neural network, right? So now we need to think about what are the techniques to reduce this overfitting. Let us try dropout and kernel regularizer to reduce overfitting of the previous model. Dropout is a method of regularizing deep neural network models. What it does is that certain input elements are randomly set to 0 and the other elements are rescaled before feeding it to the next layer. So this encourages each node to be or each neuron to be independently useful as it cannot rely on the output of other nodes. So to read more about dropout, you can look at this particular link. Now kernel regularizer is another way to do reduce overfitting. So in this case, we have certain functions called as regularizer, which allows you to apply penalties on layer parameters or layer activity during optimization. These penalties are summed into the loss function which the network optimizes. So you have the L1 regularization, L2 regularization, and you have L1 plus L2. So if you think of this in the linear regression, this thing you have lasso, ridge, and you have elastic net, right? So these are the regularizations which can be done. So it is very easy in TensorFlow to add a dropout layer. So to the previous model, after the embedding, we add a dropout layer and we say with a probability of 0.5, that means 50% of the inputs would be turned off randomly. So after our hidden layer also, I add a dropout layer, and for both the hidden layer as well as the output layer, I add kernel regularizers. So basically the L2 regularization function with the value or the penalty value. Now in the example code of TensorFlow, this value was 0.001, but when I tried with this particular value of 0.05, I got better results. So this is also an hyperparameter, the value of the regularizers as well as the dropout value over here. You can try out with different values of say 0.3, 0.5, 0.2 and see how the results are. Okay. So again, I call this as model 1, a new model, and then I do a summary and then I do a compile, which is same as before. It is the categorical cross entropy, which is the loss, optimizer is Adam, and metrics is categorical accuracy. So let's compile this. Let's again fit. We can visualize this particular model. So if you see, we have introduced dropout layers over here, right? And if you look at dropout layers, the number of input and output is same, except that some of the input values will be turned to 0, okay, and other values would be scaled. So once we fit this particular model, so I'm trying to fit over here with close to 60 epochs, again on the same trained data set with a batch of 128, and I shuffle for each batch, I shuffle the data set to get the elements of this batch. So again over here you see that there are 141 steps and the validation is done for 69 steps. So the data set size, as I said, is 69 into 128 for the validation data and 141 into 128 for the training data, right? So here if you see over here, after it starts with as usual, in the beginning you see that the validation accuracy is higher compared to the training set accuracy, but let's see what happens at the end of 60 epochs. So if you see at the end of 60 epochs, your training set accuracy is 68% and your categorical accuracy is 65%, or the validation is 65%. So they are quite close to each other over here. As usual, we can plot the history of the training and validation data loss. So if you look at the loss over here, the training and validation data loss has significantly decreased, but they are very close to each other over here. So there is no overfitting in this particular model, or the overfitting has been reduced over here. Similarly, let us look at the train versus validation data accuracy over here. So if you look at the train versus validation data accuracy also, you see that there is no huge difference between the validation set accuracy as well as the training data accuracy over here. So we have actually reduced the overfitting. But another interesting point which you will notice over here is that even after 60 epochs, the validation accuracy kind of saturates at this 65% or something. It could be a limitation of this data set as well. Now that we have created a model which reduces overfitting on the validation data, let us test this model on our test data. So this is how we evaluate the model on our test data. We pass the test sentences and the test labels over here, and we call model1.evaluate, and we get the results. So if you look at over here, it has done the evaluation. It says the categorical accuracy is around 0.66 or 0.66 or 66 percentage, and the test loss is this value over here. Now let us generate prediction on all samples. So we did not send the ground truth over here. We just sent the test sentences over here. We get our predictions, and we have to get the maximum probability of the label. So for that we use this predictions.argmax axis is equal to 1. So basically you get values like this over here for all the samples. So if you look at 0.29, 0.78 and 0.24, so the maximum value over here is 1, right? So if you look at this predict results, if you print it, it looks like 1, 2, so the index of the class. So then we convert it back to our text classes over here. So if it is 0, it means negative. If it is 1, it is neutral. If it is 2, it is positive. And then we attach this predicted results to our original data set. So that is what is done over here. So if you look over here, the original sentiment was neutral and the predicted sentiment is neutral. So for the second text over here, or the second tweet, you see it is positive and positive. But here you can see a misclassification happening. The original sentiment is positive, whereas the predicted sentiment is neutral, and so on. So this is how we predict, we create a model, and then we use the model to predict it on our test data. Okay. So now that we have created this model, we can also save it to the disk. We can also use the scalar metrics to get a classification report. So our labels are positive, negative, and neutral. So we pass the predicted data along with the original data, and we get similar results. Basically, we get an accuracy of 0.66 and the various FN scores for each of these categories. So now let us save our model. Saving this model is as simple as model.save. So model1.save, and we give a path where the model has to be saved, right? So this would write the model into our disk. So we can reload this model and again train this model as well. But here what we'll do is we'll reload the model. So basically we call tf.keras.models.load model, and we pass the path of the model where we have saved. This would reload the model, and here we can again see, if you see the summary of the model, you can see the same model shape over here. So basically we have the input layer, or we have the input layer basically, then we have the embedding layer over here, then we have the dropout layer, we have the hidden layer, then we again have a dropout layer, and then we have the output layer. Okay. So after this, we can evaluate the reloaded model on our test data, and when you do the evaluation, you see that it gives the same categorical accuracy value as before. And then we can again test it on our test data using predict method to predict the sentiment categories for this test data. So once we do the predictions, basically again new model.predict, and we pass the test sentences, we get the predictions. We again do an argmax to get the class, the sentiment class with the highest probability value, and then we do some pre-processing on these values to convert it back to our text classes. So that's what we do over here, and then when we do a sklearn metrics classification report, we see that it gives similar results. So in this way, we can actually train a neural network using TensorFlow and Keras, which is part of TensorFlow now, on text data to do multi-class classification. If you like such content, please like the video, please share the video, please subscribe to the channel. Please also press the bell icon so that you get notified whenever I am creating a new video. See you in the next video. Bye for now.